Every atom in your body was born in stars, scattered across unimaginable distances. Yet somehow, here you are, existing as one coherent person. That's the mystery of the universe. It's far more connected than it looks. Hi everyone, I'm Baham, and welcome to a short audio reading from my writing on design, the universe, and the hidden mechanics of reality. Today's episode is called Quantum Entanglement Spooky Action at a Distance. It's a fascinating look at why particles separated by light years can behave as if they're right next to each other, and what that reveals about the nature of reality itself. So let's get into the reading. Quantum Entanglement Spooky Action at a Distance. The atoms that make up everything, including your body, originated in distant stars and galaxies. That alone tells us something profound. At the most fundamental scales, we are deeply connected to the universe itself. And maybe it's impossible to separate our reality from the way we observe and interpret that universe. Introduction. Back in 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a now famous paper challenging a strange idea emerging from quantum mechanics: quantum entanglement. They argued that entanglement directly conflicted with established physical laws. Something had to be missing, hidden variables that we simply hadn't discovered yet. This objection, known as the EPR argument, became a major critique of quantum theory and one of the great debates in science. So, what exactly is entanglement? Quantum entanglement is a phenomenon where properties of one particle are directly correlated with those of another, even if they are separated by enormous distances. These particles might be electrons or photons. Their properties, like spin, exist in multiple possible states at once until we measure them. This is quantum superposition. But the moment you measure one particle, its state collapses, and the other particle instantly collapses into a matching state, no matter how far away it is. To Einstein, this implied faster than light information transfer, which was impossible. He famously called it spooky action at a distance. Modern understanding of entanglement. The EPR argument was rooted in a very traditional view of reality, a belief that objects can have definite physical properties that measurements reveal, not create. Einstein's relativity is built on this worldview, along with the principle that nothing, no influence, no signal, can travel faster than light. But quantum mechanics didn't seem to follow these rules. The EPR paper exposed a major tension. Either quantum mechanics was incomplete, or our understanding of reality needed to change. It wasn't until the 1960s that physicists had the tools to test whether hidden variables were real. In 1964, Irish physicist John Bell proposed Bell's inequality, a mathematical way to check if hidden variables were guiding entanglement. If experiments violated Bell's inequality, hidden variables could be ruled out. Fast forward to 2022. The Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for experiments that put Bell's ideas to the test, using entangled photons rather than electrons. The results were definitive. Hidden variables do not explain entanglement. Quantum mechanics predicts the correlations correctly. Entanglement is real, and it does not violate relativity. The instantaneous collapse of entangled states doesn't transmit information. It simply reveals a correlation governed by probabilities. In other words, the universe isn't breaking the speed of light. It's just operating on rules that look very different from classical physics. Conclusion. Einstein's discomfort with spooky action at a distance came from trying to fit quantum behavior into a classical local view of reality. But the EPR argument, and decades of research since, reveal that reality is deeply not local at the quantum level. Entanglement shows us that outcomes are not predetermined. Reality exists as a cloud of probabilities until we observe it. And everything around us, including us, is woven from atoms born in ancient stars. Our universe is connected in ways we are only beginning to understand. And perhaps the most unavoidable conclusion is this: reality is shaped not just by what exists, but how we observe and interpret the universe and everything within it. What strikes me every time I revisit this topic is how quantum mechanics keeps reminding us that the universe is far stranger and more interconnected than our everyday lives suggest. The idea that two particles can remain linked across vast distances challenges our assumptions about separation, independence, and certainty. And it mirrors something I often see in design and the way organizations work. Systems, people, and ideas are far more entangled than they appear on the surface. Small changes ripple outward. Observations shift outcomes. The observer effect isn't just physics, it's human behavior, culture, and decision making. That's part of why I write these pieces. They give us a language to understand complexity and to design within it, instead of trying to simplify realities that aren't simple. If you enjoyed this reading, you can find the full written version on my website at bahajabrin.com. Thanks for listening. I'm Baha, and this has been Quantum Entanglement, Spooky Action at a Distance. Until next time.